Once more, welcome everybody to the lecture of today. Today's topic is called products. Products of sets, spaces, sigma-algebras, measures. There's a quote to famous probabilist Rick Durrett that he said that product spaces is where measure theory ends and probability theory starts. So maybe we are ready to start kind of real probability related to products and, well, independence. We touched actually already independence. The Kolmogorov-01 law was actually about products already, but it was a bit hidden there. So we'll get the new, fresh point of view here. Let's start with two sets. So the thing to look is that assume that we have a set S1 and assume that we have a sigma algebra there, so we can do probabilities and measure theoretical operations there. Assume we have another set S2 equipped with a sigma algebra S2. For example, the first space could be the real line and the Borel sets on the real line. For example, the second set could also be the same real line with the same Borel sets of the real line. But quite often we need to look things together, what happens simultaneously for, let's say, for two observables. For example, if you want to study the current disease, so two relevant observables are now the number of new confirmed cases of the disease and the number of confirmed deaths. So in a way, if you want to create probabilistic models for how these two relate, there's lots of uncertainty related to reporting, as you know, so probabilistic models are needed, and then we need to connect kind of two different observables together. Well, formally, if you want to do these type of things rigorously, you need a way that kind of to connect, kind of glue two things together. So what we will do is that we join together two sets, and the way to do it is to write down the product of S1 and S2. This is the familiar Cartesian product. So it's the collection of ordered pairs with one element in S1 and the other element in S2. Well, during this phase of study, there probably is no problem about this. Just to remind you, this is a Cartesian product in the name to honor the French mathematician René Descartes, who apparently was the person to understand that, okay, we can use kind of coordinates to represent things. And another tiny remark is that parentheses here, when there are parentheses, they refer to ordered pairs. Or you could think it's a list of two elements. Yes, I assume there's nothing about this that you need to know, except that, okay, maybe you want to plot it like that. There's S1 and there's S2. If you think that you can plot them this way, so then a point in the product space is then, of course, viewed as a point in the plane, especially if you have the real line there and the real line there. So then we know that, okay, the point in the space is the R squared Euclidean plane. Then what would be the natural product of these two things? Actually, we write usually a circle there to emphasize that it's not an ordinary product. What we want is actually, what we want this to be is is a good sigma algebra on the product set. By the way, this is often called also a product space. Why space? Why not a product set? You could call it a product set also, but if you say it's space, at least it sounds more fancy. For a mathematician, if you say space, then mathematician means that it's a set with some other structure that makes it interesting to study. And of course, in our case, the other structure in probability is the measurable sets here attached with the set. So when you attach a set with something, you get the space. And then the question is, what is this? And let's look at the set. A natural thing to define this would be that we take the products of all measurable sets. So we take A1 and A2 with A1 being in S1 and A2 being a measurable set in the other sigma algebra. So this is what produces as something in the product space. So if you think that here we have an A1 and here we have A2, a subset of S2, this is a measurable set there, this is a measurable in this space. So then the product looks like a box here. So that's our Cartesian product of these two subsets. Yeah. Here we have a box, and so this should be a natural thing to have as a measurable structure for this product space. The only thing that we need to look at, this is a sigma algebra. So let's check. Is this a sigma algebra? Think about this for a little while. What do you think? Is it a sigma algebra, or do you think it is not a sigma algebra? Give me green light if you think that this is a good sigma algebra. Give me red light if you think that it's not a sigma algebra. Very good, thank you. I get more reds than greens. That means that you have been devoting some time to your quiz. So in the quiz, actually, the answer is no, not in general. So unfortunately, these boxes here. What's wrong with these boxes actually? It was in the quiz. So if you did your quiz carefully, you remember. So if you take intersection of two boxes, you get the box. But if you take union of two boxes or the complement of a box, so that may not be a box anymore. So this is the reason that this is not stable under complements or unions in general. So that's the reason that we are not going to use this. We cannot use a sigma algebra, which is not a sigma algebra. So this is called, maybe we give it a name. Let's call it R. S1, S2, a little bit tiny. Let's see, can I move this a bit? Okay. So let's call this one R for rectangles. So these are called measurable rectangles or boxes. Okay. So that's not what is a good sigma algebra. So what would be? So then we might recall that what should good mean actually? So what should we mean by a good? And what would be the minimal requirement of a good sigma algebra? So what do we want? The important map from a product space, the key map is the projection. So we can define a projection one to be, let's say this is the function which maps to S1 such that whenever we have a point in the product space, then this point is mapped to the first coordinate. And similarly, we define the second coordinate map, which is a map now to the space S2. And that maps, of course, every point in the product space to the second coordinate. So we want these to be measurable. These to be measurable with respect to our target sigma algebra, which we want to call it already with this name. This is our target sigma algebra. So the first coordinate map should be measurable from this product sigma algebra to the first sigma algebra. And the second projection should be also a measurable map, so it should be measurable to the second space. So that should be the minimal requirement of what we want. What else could we want? So this could be wish list item 1, item 2, and the wish list should be maybe that measurable boxes should be measurable. Because why else call them measurable if they are not measurable? Okay, what does it mean, to be precise? It means that every member of this collection R, S1, S2, should also be a member of the sigma algebra on the product space where we want. So we have two wishes that we want. Now, if you remember the generated sigma algebra thing, given any collection of sets, you can always define the minimal sigma algebra that contains these sets. This is what we are going to do. So, or in case 1, we can think that these are mappings from space to another space, and we want these to be measurable. We have this target measurability here, so this leads us to definition 1, that we want to define this new sigma algebra as the smallest sigma algebra, which makes these two functions measurable. In the same way as we wanted, we had two random variables. We wanted, okay, what's the smallest sigma algebra that makes this random variable measurable? So this is what we can do for given any functions to some measurable spaces, S1, S2. So that would be the minimal thing. On the other hand, for the rectangles, so the minimal thing could be that if you take minimality using the rectangles, so then we would say that this is the smallest sigma algebra which contains the collection of these measurable rectangles. Here we have two natural definitions. Which one is the right one? Both, because they are the same. And this is called the product sigma algebra. of S1 and S2. And let's state this formally as a fact. Is it clear, or do we need the proof? Who thinks this is obvious? Give me green light if you think it's obvious. Okay, one thinks it's obvious, but not all. Maybe I wouldn't think of it as completely obvious myself either, but let's maybe, to be on the safe side, let's sketch a proof. So let's prove that case one is that let's prove that this is contained in this rectangle sigma algebra. Why would this be the case? Take anything there. So what is there actually? So this is the smallest sigma algebra that contains all the pre-images of the projections. So if you take any pre-image, so let's say let's see if I can make it on the fly. Take any A1 which is measurable in S1, and let's look at the pre-image by the first projection. So what's the pre-image of this set here? It's good to look at the picture. So this is our product space, and then what's the pre-image of A1? So if A1 is there, what is the pre-image of well, for this projection? So the pre-image is then this full slice here, and that slice is equal to A1 product, the full second space in this way. And then if you look at this one is in measurable, it's an S1, and this one is in S2 calligraphic, yeah, because the full set is contained in this sigma algebra. So this product is a member of, it's an instance of a rectangle in S1, S2. And that's why actually.
I have a question.
Please.
Yeah, so the pre-image of that set wouldn't be the collection of all sets such that the first component is A1? Not only that rectangle, but the collection of all rectangles such that
let's see.
You know, because I think here you wrote the pre-image of an element is another element, but in general is a set, right?
Yes. Let's maybe I should write this in other form. This is the collection of S1 and S2 such that the projection to the first coordinate of S1, S2 belongs to A1. That's the definition. And then if you look at this in a different way, it's the collection of points S1, S2 such that the first coordinate is in S1, is in A1. And then if you think, okay, then you can take all the points in S1, A1 and then any point S2. So then that's why you can write this as a product of two things.
Yeah, okay, I see it now.
So
yeah,
maybe
I
now
was slightly confused. Yeah, thanks.
Yes, thanks for the question. So the pre-image is a set, and here is the set written using the set notation. But when we work with sets, and then we also work with set families, so then sets are also members of these set families. And here we have a set which is a member of this set family. And this set family, what is the conclusion? Let's make a bit of space here. What do we conclude from this is that that actually every pre-image of the first coordinate projection is, or let's say every pre-image of any measurable set by this projection 1 is a rectangle, so it's a measurable rectangle. And especially it is in this sigma algebra generated by these measurable rectangles. Well, the same is of course true then for the other coordinate projection as well. So if we do by symmetry for the other coordinate projection, we get the same conclusion. So actually, if you look at this projection map, so then these are measurable with respect to this sigma algebra. So we conclude that these maps PR1, PR2 are measurable with respect to this right-hand side, this sigma algebra here. And then if you think, okay, what was the definition of this set? It's defined as the smallest sigma algebra that makes these two things measurable. So, and here we have a sigma algebra which makes them measurable. So then, and here we have by definition the smallest such sigma algebra. So that's why the smallest thing should be smaller than that. So this is contained in this sigma algebra. And so that's why I can briefly write that the claim 1 is okay. What about the other direction? This direction. Now we think, okay, then we should look at the rectangle, a measurable rectangle. So let's look, what can we say about the measurable rectangle of the form A1 times A2? With A1 being measurable in S1 and A2 being measurable in the S2. Then what? Let's look at the picture again. Actually, let's make some space. So let's clean this part, which we already proved. Let's clean this away. And think about the other direction. So the other direction, one was done. So now we need to do case 2, which is now the reversed setting. So now we reverse this. And then what? Sorry about this. What do? We fix a rectangle and we see what can we do next. Now look at the picture. A rectangle, again, it's a box of this form. So what should we do now? We should think outside the box in the way that continue this box this way and look at what's there and look at this strip, and then look at that strip as well. Let's extend the box in this way as well. Here's another strip. What is the strip on the top? That strip is A1 times the full space S2. What's this horizontal strip here? If you think of this red thing here, what is that strip? That strip is not A1, not A2, but S1 times A2. Yeah. And what is in the middle? In the middle is the intersection of these two strips. Yeah. So with this picture, we know that actually A1 times A2 can be written as the intersection of set A1 times S2. That's the first strip. And then we take intersection with this other set S1 times A2. That's your black box. What then? What then? I'm thinking of black box. There's in Eindhoven, there's a student restaurant called Zwarte Doos. That means black box. I think it's an excellent name for a pub. But anyway, so for this black box, what should we recognize about this? This is a pre-image of with the projection map 1 of A1, and this is the pre-image of the set A2 for the second coordinate projection. You see, here we have a representative of a rectangle here, and so because these are pre-images of this projection map, so then that's why this one belongs to the left sigma algebra. So we know that this one is a member of the left sigma algebra. And the same is true for this one as well. And intersection of measurable sets is measurable, so that's why this whole thing is belongs to the sigma projection 1, projection 2. And that's why we conclude that all rectangles from S1 and S2, or all boxes, are members of this sigma algebra, PR1, PR2. And again, we look at the smallest sigma algebra with this property that these are contained in the sigma algebra. By definition, what we have here, this is the smallest sigma algebra that contains all the measurable rectangles. This is one sigma algebra that does contain the rectangles, so then it contains also the sigma algebra. This is why case 2 follows us again. That's the end of the proof because we did the both direction, and now we can replace this by equality as was the claim. Questions here? Very good. So this is a game of projections that we play in this way. Let's clean. That way. Okay. And maybe that's, yeah, well, let me say this is the conclusion of the definition of a product sigma algebra. It is the smallest sigma algebra that makes the projection maps measurable.